Good morning, everyone. My name is Peter Turek, and I'd like to introduce my co-presenters, Dan Watkins from Bornquist and Phil Davis from HOH Water Treatment. I've known of Dan of over 12 years. Phil, we've been communicating for the past almost 10, but I've known of HOH Water Treatment since I started my years as an operating engineer back in 1988 at the Standard Oil Building, Aon Center in Chicago. 2.5 million square foot office high-rise. And I'm sorry. And Phil's boss, Tom Hutchison, who was a president until he retired 2 years ago, was our water treatment tech. Very knowledgeable individual, very smart, very proactive. He took the company from a regional company, made it a national company, and HOH has assisted my services across the country numerous times. I'd like to thank you for coming today for this presentation. Boilers, why commissioning is crucial for proper operation and training. And we're going to cover condensing boilers, ideally, and their water treatment, and why it's important and what's necessary. This course is registered with the AIA. You will get credits for taking the course. Course description. Today we will explain the difference between condensing and non-condensing boilers, proper water treatment, safe operation, and why commissioning is essential for proper and safe operation. Part of the areas that I've done commissioning in is in the Houston area, and one of the companies I was doing work with, design engineering firm, they were very big on hybrid boilers down here in the Chicago or the Houston market. And I was trying to explain to them, you can go straight condensing boilers in the Houston area, but it took a while to get that through his mindset. His coworkers were already preaching the gospel on that aspect, but it just took a while. So it's just, if you run into a design engineer that has a mindset like that, just have a conversation with them. Our learning objectives: learn how a manufacturing representative can provide value to a boiler system replacement, understand the technical steps needed to properly test and treat a closed or open loop system, comprehend boiler applications and how to improve boiler efficiency from proper installation and water treatment, realize why proper commissioning is an integral part of any good boiler maintenance program. Introductions. I'd like to introduce Phil. Let him.
So I'm going to start us off and talk about the different types of boilers, just kind of make sure we're kind of all on the same page, understand what's out there. What determines efficiency? So we'll dive into that a little bit later. Designing and operating efficiently, right? It's not enough to just pick a high efficient boiler, install it, and then forget about it, right? There's a lot of things that go into making it actually run efficiently rather than just, running like any old boiler, right? So we're going to talk about some of the reasons that make a condensing boiler more efficient than a standard boiler. And then we'll get into some water treatment and some other things that Phil will talk about, and some case studies as well. So when we look at boiler design, you can see we kind of start with fire, pretty old school, and then big old boiler 100 years ago, and then on the right, kind of a new, modern, high efficient, smaller footprint, highly efficient condensing boiler. So the technology of heating water has changed drastically over the years. So one of the things that I always like to point out, and we'll dive in a little deeper on this at the end of the presentation, and I could talk for hours on this, but I won't. But the thing I want to point out here is, I've got all these different graphics up here: 99.8%, 98% efficient, thermal efficiency. It's all marketing, right? Like every manufacturer, everyone that I've represented, every one of our competitors, they all have their brochures, case studies, all this information talking about how efficient their boiler is, right? And they're not lying, but there's just a lot more to it than just, oh, look, we're 99.8. Oh, well, the other guy's 98. Let's buy the 99.8, right? Like, hold on. There's more behind the scenes. So, I just want to kind of point that out don't just buy the marketing, right? Understand what's really going on, understand that the design of the system and the way you operate the boiler are really the driving factors in efficiency, right? So we'll start off talking about some boiler materials. So, going back pre-condensing, condensing is kind of the newer, really pretty common nowadays. 20 years ago when I started, condensing was really pretty new in the U.S. It was still kind of a black box. People didn't quite know how it worked or why it worked. Just, it's more efficient, let's buy it, but it's twice as expensive, right? So we had non-condensing boilers were a lot more common. They're still around, but non-condensing, cast iron, steel, copper, materials like that. Near condensing, so those are typically copper. Near condensing means your efficiency's creeping up a little bit, but you're not actually condensing. Condensing boilers, stainless steel, aluminum, there's cast iron out there, but those are the typical materials for condensing. And then hybrid boiler plants, so Peter mentioned that briefly. So that's where you're taking a mix of condensing and non-condensing in the same system, okay? To get into the difference as briefly as I can, a condensing boiler takes the flue gases and the water vapor that would be in the flue gas and makes it condense so that you can extract the heat and put it back into the boiler water, the system water, rather than that heat going out the stack, okay? If you do not condense the flue gases, you're losing about 10.2% of efficiency right there, right off the bat, right? Then you also have jacket losses and some other flue losses, and that's why a non-condensing boiler, you're like in the mid-80s, roughly, for efficiency, right? A near condensing, you get up to about 88% efficiency. And a near condensing boiler is condensing the flue gases in the stack, but not in the boiler. So you're having less losses from the stack, but you're not really recapturing any of that 10.2% that you're losing as water vapor. And then the condensing boiler is where you're trying to regain that efficiency loss, right? And there's really kind of a big key to that, which is getting the water in the boiler below the dew point of the water vapor in the flue gas, right? So if you can't get the return water to the boiler cold enough, it won't condense. If it doesn't condense, well, it's really no better than, a standard non-condensing boiler, right? So that's kind of a really, really quick, basic difference between them. The reason for the materials being different is that condensate that you form on the flue gas side is acidic. It's around a 4 to 5 on the pH scale. And if you had a, copper fin tube boiler and you were running the water cold enough to make it condense all the time, that boiler is going to be dead in a matter of months, right? It's going to fail because that acidic condensate is going to eat right through the copper. It's going to leak and it's dead, right? That heat exchanger is gone. You're buying a whole new boiler, right? That's why when you go condensing, you got to go to something like a stainless steel or aluminum. Cast iron, you generally just make the casting a little thicker. So it will wear down, but it's a lot slower than copper, so it'll last. So that's kind of the difference why there's the material change, right? So starting to take away the black box, right? It's nothing real magical. It's just a change in materials. And then the other big key between those two types of boilers is non-condensing typically doesn't modulate. They're on-off, right? They just either you're full fire or you're off. Maybe they're two-stage, right? Near condensing has a little bit of modulation typically, but they can't go too far. And then fully condensing, you could have, firing rates that have a 25-to-1 turn-down ratio. So that boiler could run all the way down at 4% fire rate, all the way up to 100% firing rate, right? And it can go anywhere in between. So I like to equate this to driving your car, right? You got a gas pedal that you can, push it down. You can kind of hold your speed. It's not like you just have to floor it or hit the brake, right? If you had to do that, that's an on-off boiler, right? We'll talk a little bit more about that later, but that's not an efficient way to drive a car, right? Floor it, slam on the brake. You want to kind of hold the pedal at the speed you want and just cruise. And then hybrid boiler plants, that's kind of mixing the two together. And the reason you might do that is if you have a scenario where parts of the year your return water won't be cold enough to make the boilers condense, why have a condensing boiler, right? So you might say, well, let's put in half the plant as condensing, half the plant as non-condensing, save a bunch of money on the front end, and still capture basically the same amount of energy savings if you went full condensing, right? Because it's really just more about its ability to actually condense. So we talked a little bit about the types of boilers. We're going to dive into efficiency, and we're going to dive into designing and operating efficiently a little bit later. But we're going to shift gears a little bit and go to some water treatment discussions, and then come back after some case study as well.
All right, like Dan said, happy Friday, everyone. Hopefully the microphone works here. One thing Dan had mentioned that I think is really important is that depending on the type of boiler you're putting in, depending on the type of metals it has, depending on the type of water you use, really depends on how successful you're going to be maintaining that asset life of that piece of equipment. And what we've seen in recent years is we've seen a move towards aluminum and different types of metals that have a greater heat exchange capacity. They can get up to temperature a lot faster. Unfortunately, those are not as good handling water, and they'll corrode and they'll fail quicker if you don't take care of them. So I'm going to talk a little bit about that. The last line that's on here, though, is actually fairly important. So well water versus reverse osmosis, and this could say soft water or DI water or anything. We all come from different parts of the country. And depending on where you're from, the water source is very different. And here in Texas, the water's horrible. In West Texas, it's not as bad here. You go to Chicago, they pull out of Lake Michigan every day. The water's always the same. It's good water. We know how to take care of that pretty consistently. Know your water source. Make sure you pick the right boiler for what kind of water you're pulling in. Reverse osmosis is great, but it's extremely corrosive. So I'm okay putting that on stainless steel, but probably not black pipe, copper, things like that. So always know what you're working with as far as your water source is a good pre-treatment portion of this. So water treatment in general, why is it important? Okay, everybody in this room protects some sort of an asset. Those assets cost a lot of money. Even small boilers, maybe it's $50,000, could be more, could be less. You want to protect those as long as you can. The average lifespan of some of this equipment could be 30 years. It could be 6 months if it fails. And ultimately, when it does fail, they're going to come looking for you or me and ask why. So really, that's the goal here, is increase that life cycle of the equipment, get your money out of that piece of equipment, and don't change it constantly because you didn't take care of it. Okay? So boiler design, the most important thing everybody here can do is get involved in the pre-construction phase and the installation phase. Your facility's putting in a new boiler plant, you've kind of given the job to somebody else to handle, and you walk in and you take it over day one when they turn it on. Was everything done properly? Was it treated properly? Were the boilers boiled out properly? Was the piping cleaned properly? We don't know. So it's extremely important to make sure you get involved with that. Normally there's a submittal or a specification to have a water treatment company involved, usually through the mechanical contractor or someone like that, the boiler installer. Make sure that's completed. Usually it's buried on page 50 of a submittal, and most people miss it. The majority of calls that I get are after a boiler has failed, or after a chiller, any piece of equipment has failed, and you find out it was not commissioned properly, it was not cleaned properly, it was not treated properly. And we're talking inexpensive stuff here to protect a piece of equipment. So basically, you want to make sure it's verified. You want to verify the water treatment has been addressed, okay? If it's a replacement, and this is very important, if it's a replacement boiler, and there's a loop of water already there that's treated, it's important to get that water tested. Because as Dan mentioned earlier, maybe your new boiler has aluminum components and the old boiler had stainless steel or copper, and that water needs to be treated differently. And the only way to know if it's treated correctly is to get it tested. We don't know. So make sure for sure when you replace a boiler, you get that water tested. New installs a little bit different. Generally, they'll clean the whole loop, all the boilers. Verify the materials of construction. Is it steel? Is it copper? Is it aluminum? One important thing to remember on those three metals is they all like different pHs. For those of you that know how steel works, steel pretty much corrodes all the time. We just try to slow it down. So does copper. So does aluminum. Aluminum likes an acidic pH. Anything below 8, if you remember high school chemistry, you always think of 7 as a neutral pH. Aluminum loves that. Steel will corrode rapidly at a pH of 7. So you have to treat those things differently, okay? Verify that the manufacturer's treatment parameters are followed. Another important thing. If there is a recommended procedure for warranty, make sure you follow it. Don't listen to somebody say, hey, no, we don't need to do that. We'll do something different. Doesn't work, okay? And the last point on here is involve a reputable water treatment company. There are thousands of them across the country. If you can't find one, you can always call one of us and we'll help you find one. Get them involved as soon in the process as possible so you can say, hey, your job is to take this, run with it, make sure it gets done. I don't have time to worry about it, okay? Now on the next slide here, we actually have a case study which talks about the difference between aluminum versus stainless steel versus copper like Dan was talking about. So I'm gonna let Peter talk about this, and it's really important, a great example of why you need to know what the materials are. And he's gonna talk about that real quick.
So this case study took place in southeast Iowa. The existing boiler was a cast iron boiler. They were going to replace it with a high efficiency condensing boiler, aluminum heat exchanger. Contractor came in, took out the old, put in the new, didn't flush out the system. I get called into the project late into the scheme. I'm looking at the water test reports for the past 3 months. Everything is same, consistently, pristine water conditions. I go out to the system, I pull a sample, the water's black. And I'm like, at that point, you know, red flags, I'll be polite, red flags go off. I contact Phil's previous boss, like I said, the president of the company at that point. He just bought a company in South Dakota, put me in touch, the guy came down and took a sample. He confirmed the boiler was going to be dead within a month because of all the damage that was already done to it because of not properly flushing out that water from the old system. That's one example. Another example will apply to the hybrid boiler plants, and that took place in Conroe, Texas. I'm working with the mechanical contractor. I show up in July. Boiler plant is operating, just was started up a week prior. I wasn't able to make the startup. But already at that point, after 1 week of operation, the non-condensing boiler pad was the color of your tablecloths. The condensing boiler was sitting there idle, concrete pad, pristine, gray, no water damage. I get the mechanical contractor, and he was as bullheaded, I'll be politically correct, as a Brahma bull, because I'm down in Texas, so I can use that reference. But he wouldn't budge. 6 months later, finally took a meeting with the manufacturer's rep, controls contractor, myself, and a mechanical contractor to finally come to the conclusion that he had the plant set up incorrectly. So if you're going to be testing a hybrid boiler plants, always make sure the condenser boiler is the lead boiler. And along with that, when you do your testing, always make sure you have the control contractor present with the manufacturer's startup rep so they get the parameters set up properly so that millivolt signal sent to the boiler to control it is appropriately per what the reset schedule is for the system.
So actually, we put a couple drawings here together with some equipment. In a perfect world, you don't slap a boiler into a building without having some equipment in place. And we actually put a few things on this drawing, and actually a few things on the next slide, which I'm going to go to the next slide, and then I'm going to go back to that. So on a closed system, which would be a hot water boiler, it's going to be a closed system, you should have some basic water treatment equipment, some basic water monitoring equipment. Number one was a pot feeder. How do I get treatment into this system if I don't have a way to enter it into the system? Pot feeders are generally cheap. They're a few $100s. Have one on your loop so you can add treatment if needed. You don't want to just run city water through your boilers. Second thing on here is a side stream filter. And what a side stream filter does is it removes any debris that's generated in the system. A closed loop system doesn't blow down like a steam boiler or a cooling tower. Everything that's in there stays in the piping. And if you think about all that water moving around, if it has debris in it, it acts like sandpaper. It'll sandblast the inside of your pipe and cause erosion, corrosion, things like that. So always a good idea to have a filter on any closed system, especially a boiler system. Corrosion coupon rack. Let's say I just invested $500,000 into a new boiler plant. Maybe I want to put test strips of metal in to verify that I'm treating it properly and the metal's not corroding. Okay? What a coupon does is it gives you a readout of the corrosion rate before you have a failure. Hey, I've got a problem before you open the equipment and see the problem. Water meter. A water meter is really important on a loop. A closed loop is closed for a reason. If you're adding water to the system because you have a leak and you don't know, you will accelerate corrosion in your system. The majority of corrosion that happens in a closed loop happens with oxygen, and we all know oxygen's in water. So the more cold water you add to a system, the more corrosion you will have. Water meter helps you locate if you have a leak, especially if you've got an autofill on the system. You may be making up water all day and not even know you have a leak. And lastly, if applicable, pumps and controllers. This is more for steam side. Most closed loop hot water boilers you can treat with a pot feeder, but some people like to have controls as well. Okay, I'm going to go back to that drawing. This basically shows an ideal installation. If I was spending a lot of money on a new plant, I'd want to have that feeder. I'd want to have that filter. I definitely want to have that water meter. Okay? Coupon rack, nice to have, but the other stuff is absolutely critical. Okay? So the most important thing, like Peter had said about the aluminum, there's ways to control corrosion in everything. There's no way to stop corrosion. We're only slowing it down. Every piece of equipment you put in will corrode eventually. Your job is to make it happen 30 years from now instead of 6 months from now. Okay? And I'm going to turn it back over to Dan.
All right, before I jump into the efficiency talk, I'm going to tell a quick little story because it plays right off of what Phil just talked about. So he mentioned, closed loop, hot water boiler system, and not wanting a lot of makeup water, cold water coming in with oxygen. So maybe this is probably about maybe 15 years ago. We were repping a boiler manufacturer, and they were telling us a story about they had sold a cast iron boiler, and it failed in about 6 months. Right? So they're like, this is incredibly difficult to do, right? So they were very, very confused. They're like, you know what, we'll warranty it, we'll get you a new boiler. We want the old one back because we want to see what happened, right? Why did this thing fail? So they get it back, they cut the thing in half, open up the castings, and it's solid with scale. Just completely scaled, no room for water flow, so, no shock that the thing failed. So then they couldn't figure out, how did this happen? So they go back to the facility and they explain, like, hey, you must have been having all sorts of makeup water. We don't understand how else you could get this much scale, right? Because it's only going to happen if you have all this makeup water with all this oxygen and that you can continually pull scale out of it, right, and deposit it in the boiler. So they did some investigation, figured out the maintenance staff at night, somebody realized that it was a lot easier to take their mop bucket and put it right underneath the boiler drain to fill their bucket versus lifting the bucket and putting it in the sink to fill it. So every single day, the maintenance crew was pulling however many gallons out of this hot water boiler, and then it would make up. So just, I don't know, thousands of gallons just constantly. So, no big shock there in what happened, right? So water meter to kind of, well, why is my closed loop system making up water every single day? That shouldn't happen, right? So these are the little details that, as facility owners and operators and commissioning agents, you want to pay attention to, because that's a big expensive failure on a really minor little thing that somebody just didn't understand what they were doing. So with that being said, so I'll talk a little bit more about efficiency. So like I said, return water temperature is one of the key factors, right? And I think this is important for building owners and operators and everybody to at least understand on a basic level, because we do see a lot of building engineers that they're used to a boiler running at 180 degrees, right? That's what they've done for 30 years. All of a sudden their building gets a whole new boiler plant. The engineers went condensing. They did some redesign. They reduced the water temperature so that it could condense. And the first thing the building engineer does is say, there's no way I can heat my building with 140 degree water. I'm going to change the set point. They bump it up to 180 and it runs, right? Everybody's happy. Everybody's comfortable. No one complains in the building. So he's, great, boiler plant works. Except it never condenses because it's running way hotter than it needs to, and it's hotter than it should be to make it actually condense, right? So you've defeated the purpose of putting in this highly efficient piece of equipment. So return water temperature, that's key. I mentioned it earlier. It's the dew point of the flue gases, right? It's in the ballpark of 130 degree water on your return, right? So your boiler's supplying hot water out. It's coming back colder because it gave up BTUs to the building. If that return is about 130 or colder, you'll start to condense. Now there's more to it than that. There's things like how much excess oxygen are in the combustion process, right? If you have too much oxygen, you'll lower that dew point. Right now it might be 120 or 110 or 100, which makes it harder to condense, right? You want the dew point to be higher so that you can condense more often, which will make you more efficient more of the time. But that's really one of the keys is return water temp. The other thing is boiler cycling, and we'll dive into that a little bit. But the idea there is, just like I mentioned with the car example, imagine you were going to drive a distance of 100 miles, right? And you had two options. You could floor it and then slam on the brake. Floor it, slam on the brake. Right? Or let's say you hit 100 miles an hour and then that's when you broke, right? So you averaged maybe 50 miles an hour. So you got there in 2 hours, right? 100 miles in 2 hours. Or you could get on the highway, set your cruise control at 50 and go 50 miles an hour for 2 hours and make that distance in the exact same amount of time. Who wants to floor it to 100 and then stop? Yeah. Yeah. Who wants to do that versus who wants to just set their cruise control and cruise, right? I know which I would do from a gas consumption standpoint, right? You're going to totally drastic gas mileage. That's kind of what we're talking about here. If I have a boiler that is on-off, if the load is small, right? I have 1 million BTUs for my building. But that's a design day. That happens maybe one day out of the year, maybe a couple of hours out of the year, maybe never, right? But it's designed for that coldest day of the year. Every other day, your load is smaller, right? And if you have an on-off boiler, the only thing it can do is 1 million BTUs or nothing, right? And so if your load is maybe 100,000, right? It's 10% of the boiler capacity. Well, boiler fires, heats up the water. The building is not taking all those BTUs, so the water temperature starts to overshoot and the boiler shuts down, right? And it cools down enough, boiler fires again, right? On, off, on, off, on, off. It cycles versus a boiler that can modulate, right? Now it can say, oh, you only need 10% of the load? I can run at 10%, right? Gas valve modulates. Combustion air fan, it modulates, right? So they ramp down, you run at 100,000 BTUs, it continues to run, handles the load, but it's not on and off all day. I will say this, solving a boiler cycling problem is more important than going condensing. So I'll kind of back that up. Who has seen any boiler manufacturer with a condensing boiler with a case study that says, you know, we went to this building, we removed the existing boilers, and they were old 80%. And we put in our boilers, and we saved 60% on the energy bill. Has anybody seen case studies like that? Because I know I have. They're all over the place. And they're not lying, right? That actually does happen. Well, if the old boiler was 80% and the new boiler is condensing, and even if it was 95% all the time, which would be rare, how did I go from 80% to 95% and saved 60? It makes no sense, right? Cycling is where that difference is. It wasn't really because we condensed. That was part of it, right? We saved some energy because we condensed. But the bulk of it was, well, the condensing boiler modulates, and the old boiler was on-off. So we didn't have this constant, on and off cycling problem. So solving that is really the majority of the battle in saving energy, right? So two things, return water temperature to make it actually condense, and then having a boiler plant that can match load without cycling. Those are really the two keys to efficiency, right? And it's important for the building owners and operators and commissioning agents to understand that, because you could design the best system, but if you operate it incorrectly, well, it's not going to do what you thought it would do. So,
like Dan said, when you're doing the commissioning on the boiler, make sure you're there when the startup tech is there for the boiler plant, you have a control contractor. And then you discuss what the reset schedule is. And when the boiler tech is setting that reset schedule up, you make sure they give the control contractor the proper milliamp signal to program the set point being set to the boiler. Otherwise, you're not going to be getting that efficiency that Dan was explaining.
Yep. So here's just a little quick graph so you can kind of see the boiler return water temperature across the bottom, boiler efficiency going up. And if your return is above 130, your efficiency's, in the 80s, give or take, mid 80s. And once you hit that dew point, that's when the efficiency really starts to take off. And the colder the water, the more efficient you are, because the more you can create the condensate, which then extracts that heat that would normally go out the stack. So, again, key point. I mentioned this already, that return water temperature is huge. And now we're going to look at this little chart here in terms of the cycle efficiency part of it. I know this is kind of busy, so I'll zoom in on it in a second. But this is ASHRAE data for Chicago. I'm from Chicago, so that's what we have. But it looks at the heating degree day hours throughout the year, and it shows the outside air temp, and then how many hours of each month your operating hours within that outside air range, right? So if we zoom in a little bit, this is kind of towards the bottom of the scale. And our design day, which in Chicago is about a -5 outside air temp. We do get a little bit colder, but -5, -10, somewhere around there. The very bottom of this chart is 100%. So what that's saying is, on the far right column, 100% of load happens when it's like -5 out. And as it gets warmer, as we go up on the chart, the load shrinks, right? The column on the left is the percentage of total operating hours cumulative. So if we look at the very top, 50% of the load. So when the building only needs half of the design capability, it's about 75% of the total hours in the heating season. So 3/4 of your heating season, the load is 50% or less. That's the majority of the heating hours, right? So while we have to design a plant that can do 100%, because nobody wants to design your boiler plant too small that it can't heat on a -5 day. But we kind of don't care about the efficiency on a -5 day because it almost never happens, right? If we're only 82% efficient on that day, who cares, right? What we care about is, 75% of the time the boilers are on, well, let's make that 92, 95% efficient, right? That's so many hours, that's where we're going to capture the savings, right? That's what our benefit is. If we kind of look at this as a chart, so this is one of the previous manufacturers we represented kind of put this together, and it's a really cool chart. So what it's showing here is this red line is like the energy usage, right? And so in the middle, you're talking that's January, February. Don't visit Chicago in February. It's like the worst month ever. Horribly cold. It's dark. It's not fun. The blue line is the energy use per heating degree day. So that's sort of an efficiency line. And what that's showing is, and actually the lower that blue line is, the better, right? We're using less energy to accomplish the same thing. So on the day where we have the peak load, we're the most efficient. This is an old boiler plant, non-condensing, think on-off, right? Because it's actually fully loaded. The boiler turns on, and it might run for 3 hours before it finally starts to, overheat a little bit because there's not enough load, so it shuts down for a while, kicks on. But the on and off cycles are really long because it's fully loaded. On these shoulder seasons, right now, April, May, September, there's a load, right? But the efficiency of the boiler plant is terrible because it's cycling too much. So what we have is sort of a peak design that's up here in the middle, and our efficiencies peak over here at the worst point, but this is where most of the operating hours are. Now, it's interesting because if you were doing an analysis of your building and said, do we really need to replace our boiler plant, right? It's 20 years old, it's non-condensing, should we replace it? You could look at your bills, you could look at how much you spent in gas, you could look at the heating degree day hours for the months, and you would probably see something like that blue line. Right? And you say, well, you know what? The reality is that dip in January, February, that efficiency we can actually hit with our existing boilers. The problem is we cycle, and so we shoot up in the shoulder seasons. So if we could maintain that best efficiency line year-round, meaning solve the cycling problem, we would capture a lot of energy savings. So if we did that, so there's kind of a purple line that touches that middle bottom point. That is, I flatlined my efficiency, right? I said, well, this existing plant can do 84%. We solved the cycling problem, therefore it runs at 84% all the time, right? We don't have the cycling problem. Now if you said, well, let's also go with a condensing boiler that can modulate, and we can get cold returns, which makes our efficiency better than that 84%. Right now we can get up to maybe 90%. That would be like this green line, right? We can get even better, and we capture a little bit more savings. And this kind of goes back to my example of those case studies. If I say, well, I saved you 60% on energy by changing boilers, maybe 10, 15% of that was the condensing. That's that little narrow band between the green and the purple line. The rest of the energy savings was those two triangles above it, right? That was solving cycling problems and then just a more efficient boiler to begin with, right? So that's kind of an interesting chart, I think, and I hope makes sense to everybody what happens there, right? So solving the boiler cycling problem, you can do it a bunch of different ways. You could go non-condensing, but a bunch of boilers, right? Instead of one big 10 million BTU boiler that's on-off, if you had 10 1 million BTU boilers, right? I have the same total BTUs, but it's broken up. And now I can run one or two if the load is small. And they'll actually run and continue running because the load is small, right? They're matching the load. So I could stay non-condensing, but help solve the cycling problem by multiple boilers, right, instead of one big one. I could do it with boiler turndown, right? So a near condensing boiler, you can typically go to like a 5-to-1 turndown. So you still don't want cold returns because you don't want to make it condense, right? That's the other trick. I can make a non-condensing boiler condense if the water's cold enough, right? You don't want to do that. Peter mentioned that, right? His example of the pad, right? So, you could do boiler turndown, so that could be going with, maybe 2-stage boilers, near condensing that can modulate, or if you go fully condensing, you can get turndowns, to 25-to-1 on a single boiler, right? And so the key is being able to match the load most of the time so that you don't have all these, on-off cycles. And then the other thing to look at is, the mass of the boiler, right? Like large mass, small mass. I've never heard anybody actually define specifically what that means, but you hear people talk about it like, oh, we sell a large mass condensing boiler. Well, is there like a volume cutout per BTU? I've never heard anybody give that information, but so it's a little fuzzy, but you can kind of tell, like we have a 5 million BTU boiler. It might have 300 gallons in it. Someone else has a 5 million BTU boiler that has 1,000 gallons in it, right? Very different. Having that water volume helps prevent the cycling, right? People have heard of chilled water buffer tanks. Chillers don't like to have small volumes to play with, right? They need a certain amount of water in the system, right? Chiller manufacturers will tell you, I need 6 gallons per ton minimum, right? If you had a chiller and an air handler and that was your only system and they're in the same room and it's a real tiny loop, you put in a buffer tank because there's not enough water for the chiller. Same kind of concept here. Boilers don't necessarily have the failure problems chillers do, but they will cycle on and off a lot if they don't have a lot of volume because it heats up too fast, right? So it heats up real fast, shuts off. So having a bigger mass boiler helps, or putting in a buffer tank. So you could use small mass boilers with some sort of a buffer tank to give it the volume, and that'll help solve it. So there's a lot of different ways to attack the cycling problem. But the big 2 points are to hit efficiencies. It's a 2-prong approach. It's getting cold returns, right? And that's operating it properly and designing the system to utilize colder returns and solving the cycling problem so that you don't, create that issue as well. So hopefully that all makes sense. It's a pretty quick explanation of it. And then we'll jump into another case study here.
So I was asked to commission a boiler plant in Naples, Florida, and it was replacing 3 existing boilers with 3 brand new Cleaver Brooks. And they were high pressure steam boilers operating at 350 degrees water, 120 pounds of pressure. First day I'm there, the mechanical contractor is trying to tighten up a 1/2-inch union on the back of the downcomber with 2 24-inch pipe wrenches. A little excessive. I asked him, I said, are those unions for high pressure steam or hydronics? He looked at me with the deer in headlight looks, and I said, those are for hydronics. I said, I need high pressure steam unions installed on that downcomer. Along with that, I want an isolation valve. The piping was for the heat exchanger so you could get a sample of the boiler water and test the system water, make sure it was in the proper water treatment requirements. Second day I'm there working by myself. I get a sample off the back of the number 2 boiler. The union blows as soon as I get the water sample. And I'm standing here, my backpack is to my left, in the direct line of fire, the water streaming out of the union. Manufactured with water, or the backpack is, it is waterproof, but it's not heat resistant. But anyways, I try to explain to the contractor, you can't put on a hydronic fitting on a steam pressure boiler, and you have to put an isolation valve. That's critical. Another case study real quick. I'm at a school district in South Chicago area. My back is to the boiler. I'm working with a new facility director who has a construction background. He has no idea on facilities, how to operate them. Boiler starts up, I hear a pop, his eyes get wide. And I'm like, this is interesting, what's going on? And he's like, the sides of the boiler just popped out. And I'm like, this I have to see. Boiler cycles off, sides pop in. And I'm like, this is cool. Let's do it again. Boiler starts up, sides pop out. I'm like, all right, I've seen enough. This is not safe. Shut it off. Start looking into it. And I'll be quick. I'll cut to the chase. What was happening was the makeup system was failed. They didn't order a makeup device. And they proceeded to go to the back of the boiler and install piping, nipples, unions, couplings, whatever they had in stock to make a transition piece from a water supply to the back of the boiler, and they were adding water that way. There were a number of operation errors that were occurring. The key problem was the boiler operator was falsifying the logs. He was putting down that it was at 15 pounds of pressure, sight glass was a half level, there was no problems, etc. So there's, if you're going to be teaching or going through a boiler installation and your training is required as a commissioning provider, make sure the operators are instructed to utilize their logs properly. Real quick, back to that boiler plant in Naples. They were coming up to the end of the month. They had a rented boiler in the parking area, and the mechanical contractor wanted to get it off the property as quick as possible because he didn't want to pay another month's rent. The boiler that had that union fail, the water in the sight glass was black. I asked what was going on, and the startup tech said, he had no idea. Before this union failed, the water I was getting out of the back of the heat exchanger looked like Mountain Dew. I've never seen lime green water in a boiler before, and I don't want to see it again. But it turned out they were having a problem with the feed system, but then the other problem was they didn't properly flush out the chemicals for the flush out program. And they still had the chemicals in the boiler, but after this union failed, we did flush it out twice, and we got clear water in there. They did have to replace some parts, along with the union, obviously, and also the sight glass, because the sight glass was damaged at that point. But what I'm getting at is, if you're going to do a boiler startup, make sure it's flushed up properly. The water coming out of it is the treated water from the plant, and that the chemical limits are within manufacturer's requirements. Going to go to Phil. He could discuss, initially filling a boiler.
When you initially fill a system, the water is going to be corrosive always because you're not treated yet. So if you do initially fill a boiler, you'd like to fill it with hot water if possible. You'd like to boil it out, as Peter said. You put a cleaner in the system, you boil the boiler, you flush it to the drain. Try to heat that water as much as possible, but get treatment in there day one. Because we know, as we talked about before, that will corrode immediately. Corrosion never stops. We're trying to slow it down. If you leave water in that boiler for a week with no treatment, you've done damage, especially at room temperature. So definitely fill it with hotter water if you can. Not as concerning with hard water initially, but eventually soft water if possible, if it's a steam boiler. So,
Nothing more to add. Thank you, Phil. Once the system is installed and operating, like it says here, upon successful completion of cleaning process, system is flushed to the city water, chemicals are added. If it's a hot water boiler, corrosion control packages include nitrates or molybdates. And make sure you do the daily tests or monthly tests at least. When I was an operator, we would do our tests every shift. And that way we made sure we were on top of things, that there was no problems. Like I said, working with Phil's previous boss, he was a great guy, very knowledgeable. He loved to share information. He was very informative. If you have a manufacturer's rep or a contractor, use them to your advantage. The better you look to the owner by giving them the tools to be successful, the more the owner's staff will be calling you for repeat business. And like Phil did explain, make sure the system has the proper equipment. Make sure you got a pot feeder. Corrosion coupon rack, nice, not necessary. Side stream filter, very, very necessary. I did a job in Chicago. They were going for they were going for lead. And they had the Energy Star rating of 86 or 88. I can't remember what it was, too many years ago. So I start walking the plant. I'm seeing red flags wherever mechanical room I go into. They're looking at the building automation system, et cetera. But I go down to the boiler plant finally. They've got 2 primary pumps running in hand at 60 hertz. Side stream filters there, but the side stream filter is valved off. They're not using it. I started asking the chief engineer what's going on. His response was the side stream filters cost too much, that there was crap in the system, and he was instructed by the water treatment individual to run the pumps in hand to constantly blast the corrosive particles through the system, damaging the coils, as Dan said. And I'm like, why don't you just buy the filters? Well, they cost too much. And I'm like, well, we have to go through this. It took another conversation, but I finally did get him on board to buy the side stream filters and utilize the equipment that he had in place. And go to Phil talking about raw water. Yep.
So really, the water treatment and the water up front, as we talked about before, is super important. Raw water from a well or municipality, in Texas mostly well, contains impurities such as solids, dissolved solids, calcium, hardness, manganese, you name it. Basically, as you heat up that water, as we all know, we've probably all seen scale at one time, all the minerals will fall out of water, whether it's a steam boiler or hot water boiler. The scale will prevent the boiler water from cooling. It basically cuts down your efficiency. It cuts down on your heat transfer.
Increase your energy costs.
Yeah, basically increasing your energy cost. So that pre-treated water is super important. It's more important in a steam boiler than it is in a hot water boiler, but it's important in both. The last point on here, reverse osmosis or water softener. The disadvantage with putting in a reverse osmosis system or a water softener on your system is the water becomes much more corrosive. So you're removing the scaling aspect, but you're increasing the corrosion aspect. So treatment becomes that much more important. For those of you that work with steam boilers, you probably have an RO or you have softeners. That's why, because we'll scale immediately. Hot water boilers, in theory, like Dan said, if they're a closed loop, you can't scale them. But if you have a huge water leak, you will. And then you need to put in a water softener or an RO. So just the water treatment overview there. The one thing that was left, Peter, back here is glycol, and I'll touch on that super quick because we don't have a ton of time left. Anybody that has to use glycol in a facility, realize that glycol is also corrosive, and glycol breaks down into an acidic byproduct as it runs through a system. If you use antifreeze or glycol in your system, it's critically important, A, to make sure you have good corrosion protection, and B, make sure that glycol is in good shape. It will break down over time, grows bacteria. Bacteria basically create waste acid, and it will corrode your system that much faster. So generally, we don't like to put glycol in boilers. Especially, we don't ever want to put them in a steam boiler. But in a hot water boiler, we generally don't put it in there. But if you do, be very careful that you maintain the glycol properly.
All right, so just to kind of sum everything up here. So, it all really comes down to, picking the right boiler, the right application, condensing, non-condensing, figure out the water treatment, talk to the people you're working with, get everybody on the same page. You don't want the contractor buying an aluminum boiler when a stainless was specified, and the water treatment guy, no one talked to him, so he treats it for a stainless because that's what was on the schedule, right? He didn't see the submittals or pay attention that it was an aluminum, right? So it's really about getting everybody on the same page, right? Make sure people are talking so things go smoothly. Design the system up front to be efficient, operate it efficiently. Hopefully everyone understands a little bit better how to do that. Include adding chemicals, right? Put the pot feeder. Don't save $300, right? If you don't have a pot feeder, you're never going to add chemicals because it's just way too difficult, right? So just little things like that. And then, of course, get a commissioner, right? Bring a commissioning agent on board so they can come on, they can check everything, they can make sure it's all programmed correctly, set up, installed, and everything's right, so you have the best shot of a boiler plant that's going to be efficient and run for a long time, right? 20, 25, 30 years, not, you bought a boat anchor that, is dead in 6 months because no one did any of these things. So that's kind of the wrap up here. So I think we have maybe 2 or 3 minutes for questions, if anybody has one. All right. Thank you very much.